We'll go to the next lecture then. We'll talk about the physics a little bit of the turbulent premixed combustion. And after that, we want to talk about a little bit physics of non-premixed combustion, but there's not much we have to add compared to what we said already. And for premixed combustion, it's different. I mentioned this is more complicated than non-premixed combustion. For non-premixed combustion, we don't need to say much more. There is, again, there's a nice analytic solution here in the notes, and maybe we'll just look at this very briefly. Really, I just want to focus on the final result, and then after that, we'll talk about modeling of premixed and non-premixed combustion. So this is an example of a large eddy simulation, actually, of a stationary gas turbine. You have fuel air mixture here coming from the left, and then there's a swirler here. You see, you get a swirling flow, and then you get a flame like this. And you see, one of the things you see here in LES that is nice is you get all these dynamics. You resolve some of these dynamics of the flow and also of the flame. So what we want to do here, we want to talk about the scales of turbulent premixed combustion. We'll review again the length scales of laminar flames. We'll review the length scales of the turbulence, and then we see how these interact. We talked about laminar flames and flame thickness and all these things, and we talked about turbulence now, Kolmogorov scale and all that. But these scales now in combustion, they interact with each other. And so that's interesting. That leads to the notion of these regime diagrams, which are very important for premixed combustion, turbulent premixed combustion. And then we'll talk about, just like we talked about the laminar burning velocity, we'll talk about the turbulent burning velocity also. And we look at some of the fundamental work that was done actually many years ago. Very interesting. Very nice work by different researchers, Damköhler and so on. So these are the scales, and they're just all listed here. We talked about all of these. We have the integral turbulent scales. These are integral scales. These are the scales of the large turbulent eddies, LT, U prime, and there's also a time scale here you can form. Often we use K and epsilon here to build these scales, and then so these are the large turbulent scales, and then here the smallest turbulent scales are the Kolmogorov scales, and these depend here on nu and epsilon. Can be written like this, and then for the laminar flames, we defined the laminar flame thickness as d over SL, or like this if we use unity Lewis number, and then there's a flame time also. It can be written like this or can be written like this. So for each one of these, you can say basically you always have two scales. You have a length scale and a velocity scale, and a time scale always follows from this. Okay, so here, for example, we have a length scale and a velocity scale, and are these two. And then the time scale you see follows from these two, and same here. And then there are these intrinsic parameters here, which are you could say K is the velocity scale, okay? And then here we have a length scale, and so here the parameter is epsilon, here the parameter is d, and then here, well, something related to these, a little more complicated to see. But now you have these scales. They would interact. We want to see how they interact. And so we define a few non-dimensional groups. The Schmidt number here, nu divided by d. We want to assume for the simplicity here that's equal to 1. We can always replace nu by d and vice versa. And then we can define a Reynolds number here. Reynolds number is, the turbulence Reynolds number is written here, I thought I had written it here somewhere, is LT times U prime divided by nu, okay? But nu is the same as D, okay? And when we look at this, then D is the same as LF times SL. Okay? So I can write the Reynolds number as LT U prime divided by LF times SL. That's interesting because you see now these are ratios here. This is LT over FL. This is the ratio of the large scale of the turbulence divided by the flame thickness. And this here is the ratio of the equivalent velocity scales. The velocity fluctuation, the large eddies, the velocity of the large eddies, divided by the flame speed, the laminar flame speed. Okay, so that's the Reynolds number. We can also define a Dampköhler number here. Dampköhler number is a flow time scale divided by a chemical time scale. We said the chemical time scale is the same as the flame time scale. And so flame time scale here is LF divided by SL. And the flow time scale is LT by U prime. And then this is what we get. And as you see again, these are these ratios of these quantities, okay, of the velocity scales and the length scales. And then it turns out that the Dampköhler number in premix combustion, we often use the Dampköhler number. For non-premix combustion, for premix combustion, the Dampköhler number is not that relevant because really the large scale of the interaction of the large scale of the turbulence and the small scale, it has some relevance, but not so much for the actual physics of how these interact. What's more important is how the small scales interact with the flame. And you can easily see why that is. If I just look at a laminar flame, let's assume I have a laminar flame, and then this would be the temperature, it's a function of x in a laminar flame. And now let's say I have an eddy, which is very large. So this is my flame thickness here, maybe this. Okay? Maybe I have now, so this would be LF, and now I have a turbulent eddy, which is much larger. Let's say it goes from here all the way to over here. Okay? So does that do anything with the flame structure? No. It will just take the flame structure and move it around, but it doesn't interact really with the flame structure. So on the other hand, if you look at the smallest eddies, if now the very smallest eddy, again, is like this, then still they don't interact. But if the smallest eddy now is of that size, okay, then it will help mixing in the preheat zone, in the reaction zone, or whatever. So how the smallest eddy interacts with the flame, that is very important. And so the Karlovitz number here, that is the most important non-dimensional group. Now for premixed turbulent combustion, that compares the time scale of the flame, or the chemical time scale, with the smallest time scale in turbulence, which is the Kolmogorov time scale. Okay? And so you can write it like this, and I can write it again, using these relations on the previous slide. I can write it like this now, LF over LT to the 1/2 times U prime over SL to the 3/2, and that again relates it back to these same velocity and length scale ratios. Okay, here we look at, you see, we have the flame thickness. I said earlier the flame thickness, but remember when we talked about the structure of flames, we said there's an inert preheat region. That's of the inert preheat region, that's of the size of the overall flame thickness. But then within this, there's a very thin reaction zone that's much thinner. Okay? So now I could also ask the question, how do the Kolmogorov scales interact with this reaction zone? Okay? So you could imagine the eddies that are much larger than the reaction zone, but they're much smaller than the flame thickness. And so they do interact here somehow with the preheat region, but not with the reaction zone. Okay? So delta here, that's the size of the thickness of the reaction zone, and so, or L delta, that's the thickness of the reaction zone. And so we can also define this Karlovitz delta, which is the thickness of the reaction zone divided by Kolmogorov length. And it turns out because L delta divided by LF is roughly 1/10, this is the same as 1/10 squared times Karlovitz. So this is typically 100 times this number. Okay, but that's just a rough estimate. So now we can use this to build these regime diagrams. This is very interesting because now we expressed all these non-dimensional groups here in terms of a velocity and a length scale ratio. And so these are the important parameters that describe the flame and the turbulence. Then we can see how these parameters look like in these for different values, let's say, of these parameters. So if you take so what we want to do is we want to have a plot, the velocity ratio as a function of the length scale ratio. Okay, so the velocity ratio here, you can see if I bring this here on the other side, then I have U prime over SL is equal to Reynolds turbulent times LF over LT. Okay. And so that would be, so this is a log scale, so that would be, so now I set Reynolds equal to 1, and so then U prime over SL is just LT over LF to the minus 1. Okay? So that's a curve that I can put in here, and then, so this red line here, that's where the Reynolds number is equal to 1. And what this means is in this region, the Reynolds number is smaller than 1, here it's larger than 1, and so this means here it's laminar and here it's turbulent. Now don't get hung up on the equal to 1. Maybe the transition is at Reynolds equal to 10, or maybe it's at Reynolds equal to 0.1. Here we're talking about scaling analysis. We're not worried about these constant factors. We're just worried about scaling. Basically, it means if I have if I'm sitting here and it's turbulent, and I make this 10 times smaller and I make this 10 times larger, it should still be turbulent. Okay, so if this was laminar, even though because this line's in the wrong place, then I make this LT over LF 10 times smaller, make U prime over SL 10 times larger, then it should still be laminar. We're talking about scaling, not so much exact values. Okay, but anyways, so that's an interesting line here already, and then we said. Maybe it's interesting also to look at Karlovitz number equal to 1, okay? Tells you which one is larger, the flame thickness or the Kolmogorov length. And so Karlovitz equal to 1, I can do the same thing, set this here equal to 1, and then I have U prime over SL is equal to LF or LT over LF to the 1/3 or to the 2/3. And so to the 1/3, I'm sorry. So I put this... So this here is a line with a slope of 1/3, and if this is 1, then this also has to be equal to 1. So they both have to go through this thing. And okay, so now I subdivide this here in different regions where in this region here the Kolmogorov length is larger. We can always say is much larger. Let's say just for the sake of getting this straight in our head, is much larger than the flame thickness. So this would be the case here where, I have a huge eddy here and a very small flame. And this here is the opposite. This is where the little eddies can get into this region. Then also we have this line here, Karlovitz delta is equal to 1. So this here is, by the way, is called the Klimov-Williams criterion. And this here I call this the Peters criterion because he came up with this line. And then there's another one here which is not so important. This is when U prime is equal to SL, so this just means this here is equal to 1. That gives you this line. Okay? Damm-Köhler would be just a line with a slope of 1. But again, the Damm-Köhler number here is not so important, so we don't show this here. Okay, so let's look at the different regimes. This regime here is called the corrugated flamelet regime. Let's look at this. This is the regime where the eddies are much larger than the flame thickness. Then this is how this looks like. This is the DNS here we did in this limit. Then the flame, if the turbulence, or this is an experiment here that was done in this limit. This here is OH pliff. And what you see here is you see the OH here, and you see no OH here, and you see the flame is very thin, okay? The flame is so thin that you always get even though you have turbulence, you always get a very clear interface, okay? This is unburned, this is burned, and in between you have a very thin flame, Okay? So in that limit then, the flame appears really as an infinitely thin surface to the turbulence. The turbulence does not do anything with the structure of this flame. Remember, my smallest eddy goes from here to way over there. And this is the flame thickness. So the turbulent eddies, they cannot penetrate the structure. They cannot destroy the structure. You still have the laminar structure of the flame. But what the turbulence does is, and that's what you see here, the turbulence will increase the flame area, the flame surface area, okay, like here, and it, will move unburned stuff from here to there and burn stuff from here to there and so on. That's what it does, but it does not change the inner structure of the flame. Okay, that's the corrugated flame regime. So here, we could imagine that this flame still propagates with a laminar burning velocity, and the influence of the turbulence is just to make the flame surface much, much larger, so that because you can imagine the reaction rate is something like the flame surface times the burning velocity, that gives you volume per time. That's the volume per time you burn. And if the surface area is very, very large, then also that mass burning rate per unit time would be very, very large. Okay, so that's how we need to think of modeling this. Okay, and then we have another regime here. That is the regime now where Karlovitz delta here is larger than 1. If Karlovitz delta is larger than 1, that's what we call the broken reaction zones regime. In that limit, the turbulence is so small that the turbulence is much smaller than even the inner layer thickness. And so what it will do is it will just mix the inner layer, disrupt the inner layer, and so on. Let's say you produce a radical, it will just take it away and move it somewhere else. In that limit, you don't find a coherent reaction zone anymore, and typically flames extinguish. They don't know what to do anymore. Typically, that's a regime that, as an engineer, you would avoid. Why would you avoid it? Not because you looked at this thing and you said, well, I should stay away from U prime over Z equal to whatnot and this and that. You would avoid it because if you build a combustor where the flame always extinguishes, is not a good combustor. You would say, let's go back and do something about it, decrease the velocity or make the temperature higher so that the burning velocity is higher or whatever. You would just, by being an engineer, figure out, a flame that burns. And so this regime is something that is, in practice, is hardly ever encountered. You guys keep me busy in the break, so I have to take my breaks in the lecture. So this is an example. This is from a DNS here of Aspden and Bell at Lawrence Berkeley lab. So this is a very, very high. So this is low Karlovitz number, and this very, very high Karlovitz number. And you see here on the left, you have the burning rate, and you see Karlovitz number is smaller than 1. You get a thin flame sheet, and this temperature. This is the same thing we saw in the experiment. And then here, when you go to very large, you don't see a thin flame sheet anymore. It seems like things are more distributed. So sometimes it's called also distributed reaction zone regime. Okay, then there's the regime here in between. Turns out this is the regime where most of the practical applications live. This is what we call the thin reaction zones regime. And that regime, you have the smallest turbulent eddies get smaller, and they're smaller than, so the Karlovitz number is larger than 1, means the Kolmogorov scale is smaller than the flame thickness. But at the same time, Karlovitz delta is smaller than 1, which means the Kolmogorov scale is larger than the inner layer thickness. Okay? So what this means is the inner layer, this is where all the chemistry takes place and all the, the conversion from fuel to product, which is where the fuel disappears and the hydrogen radical and all of these things. So all the chemistry stuff happens there, but the turbulence doesn't do anything to that. It just takes that entire layer and it moves it around. It moves it from here to there, but it doesn't penetrate this inner layer and mess up the structure that we found. So, on the other hand, the inert preheat region, that is now controlled by turbulence. You have, because the turbulence, the small turbulent eddies, they're smaller than the preheat region, so you have turbulent eddies mixing within the preheat region. So we said earlier on, in the preheat region, what's important is the transport of heat to heat up the unburned reactants, and also the transport of the fuel and the air, into the reaction zone. And so that is now supported by the turbulence also. Okay, so what you have is chemically it seems to be still exactly the same, but the transport process is enhanced, is made faster by the turbulence. Okay, so that's how when we think of modeling, that's how we need to think about it. Here's an example. This is also from a DNS that we did. So here you have this is the burnt region, this temperature, let's say, and this is the unburnt region, and then you see that you still get a sharp interface here, okay? But in the preheat region, you get, this is the preheat region is broadened by the turbulence, and you see, for example, if I look in a slice here, you see that the temperature here goes up, goes a little more up, and so on. So rather than having a thin flame like this, maybe I have something that looks like this. Okay, and then the reaction zone maybe would still be here. Okay. So that's then the corrugated filament regime. This here just shows the this DNS here by Asplin was done at different values here of U prime over SL. This shows where these are. This and this one are the ones, I guess. No, we looked at an even lower one earlier. But these are these four cases. Okay, one is in the thin reaction zones regime, one's just at the border, and two are in the broken reaction zones regime. And you see these, so this density, burning rate, and temperature. If you just look at the burning rate, this would be the low, and then here you go higher and higher in the Karlovitz number. Then you see here, you still see, if you just look at the burning rate, you still see a thin sheet. Here you see also a thin sheet, but it's more corrugated now. It's not totally distributed, it's just more corrugated. And then here it starts to be more distributed, and here even more. Okay, and you see the same thing here, also in the temperature field. Okay, so now we thought already about how to model this. First question is, do we need to model this at all? Can we just say the turbulent burning velocity is the same as the laminar burning velocity? And so we can look at this here. This is, I mentioned this earlier, this is from these fits that we had. This is the burning velocity as function of pressure, and then the different lines are different preheat temperatures. Okay, this is for isooctane. Now, if you're in a gasoline spark ignition engine, then you have a compression stroke, and in a compression stroke you have a let's say an isentropic compression. So if you start here at 298 Kelvin and 1 bar, and then you do this isentropic compression, you end up here at 20 bar and what is this here? About 500 Kelvin. About 700 Kelvin. And this the burning velocity you get is like, let's say, what is this here? 60, 70, 80. Okay, and here it was 40. So that's what I said in one of the previous lectures. In this engine, you have strong preheating, and the strong preheating, it will change the adiabatic flame temperature, and that is very, very important for the burning velocity. The burning velocity goes up. At the same time, the pressure decreases the burning velocity, and so you see the overall effect of this compression is not as strong that you get a totally different order of magnitude. So let's say we have here a burning velocity of like 80 centimeters per second. Now on this side here, you see from an engine experiment, transparent engine experiment, you see the evaluation here of the burning velocity, the apparent burning velocity you get. I don't know how this was measured. There are two different ways how you can do it. You can either have a transparent engine and just look at how the flame moves, but you can also just from the pressure trace, if you just measure pressure and you assume you have, kind of a cylindrical or spherical flame, you can also, infer what roughly the burning velocity is. And so you see here is roughly, at this speed here, it's roughly 15 meters per second. So here we have less than 1 meter per second is the laminar burning velocity at these conditions, and 15 meters per second is the measured one. So it's very obvious. No, you cannot neglect this. This is a huge effect. It's more like this is a factor of 15 or whatever. So it's a very important thing to measure, to model. Okay, I don't actually know what this is, so I'll skip over this. This student put this in, and I was looking at this yesterday to see if it makes any sense, but it didn't somehow. So, right. So we want to model. We want to think of how can we model the burning velocity. There are different regimes, and what's important here is, and that is really important. As we saw earlier, the physics in these different regimes are very, very different, okay? In the one, you kind of have a laminar flame, and it's a little corrugated or whatever, and in the other one, the whole flame is messed up. The preheat region is messed up, and so on. These things need to be taken into account. This interaction needs to be taken into account. So a model should always know what are the real physics that are going on, and then consider these models. So it's very hard at the same time then to have a model that is applicable to anything. You want to have a model that can be applied to non-premixed combustion, premixed combustion, partially premixed combustion. In all of these different regimes, you can imagine it's not a simple task to come up with a model like this. You can say, oh, maybe my model shouldn't care about all these microphysics, but I think that would not be right, because if you don't consider the microphysics, you would say they are either not important. You would say they're not important, but they are important. Okay, so Damköhler, of course, realized this. He was a smart guy. 1940 here. He came up with models for this, and it's intriguing how insightful these models were, even in the 40s, where really, you didn't have much laser diagnostics and stuff like this. I don't think they did DNS at the time, even. So I think the DNS they did at the time was with a pencil on a piece of paper or something. So they spent less time debugging their computer code and looking at vast amount of data, and spent more time just thinking about it. And maybe we should do that also sometimes. Anyway, so he came up with two different models. He called the large-scale turbulence limit. We can identify this now with what we call the corrugated flamelet regime. And the second one here is what he called the small-scale turbulence limit, and that's what we identify now, what we call now the thin reaction zones regime. So this is what he did. Essentially, I tried to prepare you for a start process already. Take the corrugated flamelet regime. We said the structure of the flame is not disturbed. It still moves with a laminar burning velocity, but at the same time, the surface area is largely increased. So you have, this is the instantaneous flame. It burns with a laminar burning velocity, and it has an area here, which we call AT, A of the turbulent flame. Okay, it's unburned is burned, let's say. But then now we want to model this. So we say we don't know about all the little fluctuations. We just want to say this should be a planar flame that moves now with a turbulent burning velocity, and we need to know what the turbulent burning velocity is. But if I equate for both of these, I equate the mass burning rate. So the model should be such that the planar flame with a turbulent burning velocity, of course, has same mass burning rate. So if I equate the mass burning rate, I get AT times SL. I said earlier that has units volume per time, so that is the volume I burn, and then times the density, that would be the mass of fuel I burn per unit time, or let's say the mass of unburned mixture. And then on the model here is the mean density times ST times A. That also gives me the mass burning rate. So if you see that ST over SL is then equal to the area ratio, and that makes perfect sense. Okay, if we assume that the density here is still the same. Okay, the question now is, can I relate this also to my, the velocity? Velocity is something I know usually. Can I relate this to the velocity? And what he did then was he looked at the Bunsen flame. Take the Bunsen flame. We said that in the Bunsen flame, we said that the SL over U prime, we said SL over U, the incoming velocity, that's equal to the sine of alpha here. And but then sine of alpha at the same time also is this here, this length divided by this, okay? So I could say AT, so if I approximate my turbulent flame here, if I approximate this with a little Bunsen flame, I could say this area here divided by this area, the nozzle area in that for the Bunsen flame, is the same as U prime, U, the incoming velocity, over SL. And because U prime is proportional to the incoming velocity, you could say AT divided by A is equal to or is proportional to U prime over SL. So then ST over SL is nothing else than U prime over SL, or the laminar burning velocity plus U prime over SL. And you see that then ST, basically, if you forget about this 1, if you say this has to be a factor much, much larger than 1, we said earlier it's 15 or something, I forget about this 1, let's say, then ST is equal to U prime, okay, or is proportional to U prime. That's very interesting. We'll see later on that that's actually is proportional. The coefficient of proportionality is roughly equal to 2, and this is it's quite accurate actually. This is interesting because you could think, if you take the opportunity, you could think, how does a piston engine work? It works at very low speed, okay? At very low speed, I need a certain time for the whole mixture to burn out. But then at very high speed, the combustion process all of a sudden needs to be much faster. How does that work? I mean, why does an engine work at very low speed and very high speed? There are engines that work at 20,000 RPM. There are engines that work at 500 RPM. Okay, how does that work? Now, U prime actually is proportional to the piston speed. Okay, the faster the piston is easy to imagine because that's the only velocity scale you have now. Is imposed by the engine is the piston speed, and the U prime, that's proportional to the piston speed. Okay, so if the piston is much faster, higher RPM, then U prime is much larger, and the flame burns much faster. The flame always knows this is how fast the piston is fast, I need to burn faster. Isn't that beautiful? Wondering if Otto was thinking of that. But apparently not, because it's 1940 and the engine had been running before. But sometimes you get lucky in life. But this is very interesting. So if we then compare that with experiments, this is a form that's often used here. ST over SL is an empirical form that's often used in models, is 1 plus some constant times U prime over SL. This here, by the way, the 1 we always add this if there's no turbulence. Okay, in the limit with no turbulence, U prime is 0, and then ST should be equal to SL. Okay, so that's why we just add this 1 at the end to satisfy that limit. But that shouldn't be important for very strong turbulence. So if we do this, so the exponent n here, it varies. Now for us here, it's equal to 1. And if you make it 1, then you see this is what it is. So for this regime here, you see this linear function actually is really good. But then for large V prime over SL, you see, it bends off, and this is not accurate anymore. So that is really when we get to the limit that Karlovitz number now becomes larger than 1, then this is not correct anymore. Okay?
What do these points correspond to, like different kind of views?
I don't know actually. I think these are all just different experiments. And you see there's a lot of scatter in these experiments. And that is because sometimes it's very hard to control. These might be experiments from the group of Derek Bradley in Leeds. And they have also a spherical combustion chamber. It's turbulent. Or let's say you have a kind of a spherical flame, turbulent. This one here in Princeton also. And so you measure what's going on. But if you start burning a flame, then all the things we said here, they're really only true if you have kind of equilibrium turbulence. It's not when you start a shear flow and you don't have turbulence. We say, the turbulence is kind of proportional to the velocity gradients. Well, that's not true in the beginning. That's only true once you have an established, flow where the dissipation and the energy transfer and the energy production is all in equilibrium. Same with a flame. If you start, let's say you have unburnt mixture, and then you start a flame, you ignite a flame, and you have a little flame kernel. That's not turbulent yet. It first needs to interact with with the turbulence. So the initial conditions for these are not always all that well controlled, I think, and so that's why you get a lot of scatter. So we shouldn't see. I mean, this is a trick here. In a plot like this, you see the points are all over the place. If I want to see that this linear line is right, I can see it. If I want to see that this curved line is right, I can also see that. So the other thing is this, and we'll see that in a minute. This here plots ST over SL as function of V prime over SL. We will see in a minute that in this regime, where Karlovitz number is larger than 1, it's not only the velocity that's important, it's also the length scale that's important. That is not considered here. So this is another reason why you get so many, such a big scatter, because you have 2 parameters, but this shows it only as function of 1 parameter. So this should be conditioned then also on the value of the second parameter, and maybe then, you would see that this here is something that really should be in these experiments, something that really should be in the corrugated flame regime, and these should really be in the thin reaction zones regime. Okay? Okay, so that was the corrugated flame regime, a model for the corrugated flame regime. Now, this is what Damköhler did for what he called the small-scale turbulence regime. He also realized in that regime, maybe the flame structure, it doesn't change, but the transport, or he assumed the chemical timescale doesn't change, but the transport is enhanced. And so in laminar flames, we said SL is equal to the square root of D over chemical timescale. And now, this is interesting, we can say, okay, so that's what he did. He said, okay, now if the transport is now really a turbulent transport, then I should replace D by dt. And if the chemical timescale, well, he said that shouldn't be changed, maybe. And so if I replace the chemical timescale, it stays the same. And for the turbulent burning velocity, I just take the same scaling relation, but I replace the diffusivity by a turbulent diffusivity. And if you do that, you can bring it back here to these quantities. dt is just like this, is u prime times lt, and times some coefficient, and then tc I can write like this, and then again I have this as function of this ratio, and you see that this here actually is the Reynolds number. This is the turbulence Reynolds number. Okay, so well, you can combine these two in, and what's important here, that's what I just said. You see, ST in this regime, it depends not only on U prime, it also depends on the length scale ratio. So a formula like this can actually not be right. I mean, the N and C, they kind of have to depend on the length scales. Then it can be right, of course. But if these are constants, then in that regime, this cannot be right. Or not be general or whatever. So you can combine these two limits in one formula. This is here by Peters. So if you take this, you see this is a quadratic solution of a quadratic equation depending on the length scale ratio and the velocity scale ratio. And if you take this here in the limit of large Damköhler number, then you get this. And if you take it in the lit of very small Damköhler number goes to 0, then you get this. And so that, that shows that then this formula, it recovers both the Damköhler small scale and large scale limit. And now if you compare that with experiments, then again, these are experiments now plotted as function of Damköhler number. The nice thing is you can rewrite this if you take the same formula here, this ST over SL. If I write this as ST over U prime, then I can write it as a single function of a single parameter. Of course, because I have two parameters, I put one on the left-hand side, and there's only one left. So I can plot then this ST minus SL here divided by U prime. I can plot this as function of the Damköhler number, and that now should be, let's say a universal function. All these individual points here, these are individual experiments, and you see again there's a lot of scatter, but if you take the conditional average here now at each Damköhler number, then you get these big points, and then this black line here, the solid black line, that is this model, and you see the model is not so bad. It's actually pretty good. Using here, this is interesting also, using here these coefficients, I said this earlier, proportionality coefficient is equal to 2. That's actually pretty good. And here, proportionality coefficient is actually equal to 1. That's also pretty good. So you see this is the large-scale limit. You see how this asymptotes to this value of 2 that we're just looking at. And in the small-scale limit, you get this nonlinear behavior here. Okay, so that's kind of the something about the physics of premixed turbulent combustion, where we have two different regimes, large scale and the small scale regime, and we identified, using the Karlovitz number as a parameter, we identified these different regimes in this regime diagram, where we said the different regimes are the interaction of the smaller scales of the turbulence with the flame. Either the small scale is much, much larger than we're in the corrugated flame regime, or it's small enough that it penetrates into the preheat region, but not in the reaction zone. That is the thin reaction zones regime. And then we have if the turbulence scales become smaller, then they might enter the inner layer, or the inner layer becomes thicker because you go more lean or something. And then this is what we call the broken reaction zones regime. So why did I say earlier, the thin reaction zones regime, that's where you find typically, or most of the applications? Any thoughts? Yes, stable, but that could also be corrugated flamelet regime. That would also be stable. No local extinction and things like that.
Because of high pressure?
No? No. I mean, what you could measure is not how people design.
You're enhancing the mixing in the preheat zone?
Right. So if you want to increase the mass burning, the mixing, you want the turbulence to be stronger and stronger and stronger. But you make it too strong, then the flame goes out. Okay? So what you do as a designer, you would try to make a combustor such that you get the highest possible mass burning rate at still stable combustion. Okay? And that is right in this region where you are just below maybe the transition to the broken reaction zones regime, which is right in the thin reaction zones regime. Yeah, so it just burns faster, but not so fast that it will extinguish. Okay? So, let's move on to the next lecture then. So, for non-premix combustion, people have also developed these regime diagrams, but they're not, I mean, this here is something I should mention. This originally was called the Borghi diagram. It was, invented by Professor Borghi from France, and others had different diagrams. The reason why this one was so successful is you can imagine you can put different quantities on your axis. Using the velocity and the length scale ratio, that was ingenious because that's what people understand. We do understand velocities and we do understand length. We have an intuitive feel for this. So this is why people always look at this Borghi type diagram, which then later on was modified by Peters with his second Karlovitz delta criterion. Is this the best way to look at it? No, it's not the best way to look at it. There are better ways to look at it, at least I think, because we have our own regime diagram that we developed for LES. Maybe I'll show this later on. I'm not sure if it's in the notes, where we use the Karlovitz number as one of the axes. That makes a lot more sense because really all we did when we discussed this, we didn't discuss U prime larger or smaller. We just discussed the Karlovitz number. The Karlovitz number really is the quantity that is important for the physics. Okay, so we might look at this later on. Anyways, so for non-premix combustion, people also have looked at these, have started talking about these regime diagrams, but they don't have the same meaning. Here we said in whatever limit we are, we need to think a lot to come up with these burning velocity models, even in simple, we make simplifications. On the other hand, for non-premix combustion, is not so hard. We say, well, if a simple limit, infinitely fast chemistry, then everything is just determined by mixing, okay? Just solve the mixture fraction equation, maybe the variance equation, and everything's good. So here we don't have much more to add about the physics. There's one thing that I thought might be interesting here, which is the flame length of non-premix flames. And what's interesting is that if you change the Reynolds number, then the question is, what happens with the flame length? What do you think? What happens with the flame length if you increase the Reynolds number? So how do I increase the Reynolds number? I just increase the flow velocity. Okay, how does the flame length change? If I increase the velocity, you think it gets shorter? Shorter is what he says. And who thinks it gets longer? So if I decrease the velocity more and more and more until it's almost no fuel is coming out, you think it gets longer and longer? You think it stays the same or gets shorter? Shorter. So we have, did anyone say it stays the same? No. Let's see what our burner does. Think of okay, so we can even I don't know, these used to have a thing here to adjust it, but so let's start small. Okay, small flow rate is very short. Okay, increased flow rate, it gets longer, so some of you were right. and then I increase even more. And I think I can't increase it more. It doesn't really get turbulent anyways. But anyways, so let's look at this was just for, taking a little break for you guys. So there is an analytic solution for the flame length. And because we said, you take the cigarette lighter, for example, because we said, infinitely fast chemistry, it will burn just at stoichiometric. And then because of mixing, stoichiometric will look like this. Up here, it will be all very, very lean because the fuel has all mixed with the air. So where the stoichiometric surface crosses the center line, that's kind of the flame length. That's a good measure for the flame length. So in that case, then, we only need to look at the mixer fraction field. This, by the way, is a candle. And here, by the way, also you see the blue reaction zone up to the point where this gets very light. And this flame in microgravity. So microgravity, it's just a sphere in a sense. But this is candle, so it's this is buoyancy dominated. If you have a flow that is momentum dominated, so you have a flow coming out like this, then the buoyancy might not be so important. So anyways, we have continuity, momentum equation, mixer fraction equation, and really all we want to do is we want to determine the mixer fraction field. And then, I'll go through this very quickly here. We make some simplifications, and we introduce, so we know or we assume there's a similarity solution, and so we introduce similarity coordinates here. Zeta here, that would be a coordinate measuring the axial distance along the center line, let's say, or in downstream direction. Eta here is a radial coordinate, but you see it's a similarity coordinate now. And so then, as we said last time, analysis is always good to introduce stream function because then the continuity equation goes away. So here we introduce stream function again, and then satisfies the continuity. Then we have transformation rules. We transform the system of equations into these similarity coordinates. Then we get let's see, this is just transformation rules. This is the non-dimensional stream function, transformation rules. And then we get an equation like this here. And then a simple trick. So you have a lot of terms, simple trick. Now we have to say if a similarity solution should exist, then this stream function cannot be a function here of zeta anymore. That's the condition for, so basically the solution, the non-dimensional solution now cannot be a function of the nozzle distance anymore because the similarity solution says the scaled solution has to be the same everywhere in the field, okay? So that means this term here goes away. I end up with a simple equation here, is this, and then let's see, I can do the same thing for the mixer fraction. Here this is the omega, that's the normalized mixer fraction. And I can solve these equations analytically, and I get this. This here is then the stream function. So basically velocity field, this mixer fraction field. I get these two relations here. You see they look fairly simple. I get these gamma constants here. Gamma, these are integration constants, which have not been determined yet. I can determine these by this constant. I can determine this for the momentum field just from momentum conservation. I know the momentum I feed in, and I know momentum is conserved, so I can determine it everywhere else. This is then this gamma. I plug this in, and I do the same thing here. Mixer fraction also, mixer fraction flux also needs to be conserved. So this is the constant I get from this, and so I plug this in, and here's my final solution. So ZA, this is the mixer fraction on the center line. That is equal to this here, where the zeta, that was the distance on the center line. If I set zeta equal to L, or I set ZA of Z equal to 0, or stoichiometric, then I can compute the L from this, and it gives me this. So this is the final result here. This would be valid for a laminar flame without buoyancy, so a momentum-dominated flame. And all we want to look at is how this looks like. So first of all, you see that the flame length for this laminar flame, you see, so I take L divided by D. D is the nozzle diameter. L divided by D is then proportional here to the Reynolds number. Okay? So the larger the Reynolds number, the larger the flame length. That's exactly what we saw. And actually it's linear. If you double the speed, then you double the flame length. Okay? Interesting result. You also see that it depends on this transport coefficient. C is this Chapman-Rubezine parameter we had yesterday also. It depends on Z-stoichiometric. Z-stoichiometric, you can modify this by diluting the fuel, for example, or enhancing the oxygen in the air or something. That would change Z-stoichiometric. And for different fuels, it's different also, but it's not so much different. So, maybe for burning fuel in air is very similar for different hydrocarbon fuels. Okay, so we see this is, but is this the full story? No, because we said we want to talk about turbulent combustion also. This was for laminar flames. And so what we see here is L divided by D is proportional to the Reynolds number. If we look at, so this here is a plot that comes from experimental data. And what you see here is for small Reynolds number, you see this linear relation here is quite good. We also saw this here, basically in our little experiment. Okay, now we can look at the turbulent flames in the same way. You see, in turbulent flames, we assume here the spreading rate is linear. And this is my little example here. This is a German soccer coach, by the way, or used to be German soccer coach. In a game, very nervous, smoking a cigarette, and you see this is a turbulent jet here. No, I mean, seriously. You see, these are just two linear lines. I just put these lines there. This is perfectly linear, okay? The linear relation here just comes from basically momentum conservation. Momentum conservation and turbulence leads to the fact, turbulence scaling leads to the fact that this here is linear, and you see is not a bad assumption. Okay, so now we have the same equations, except that here instead of the molecular, we have the turbulent viscosity. So the equations here are compared here with the laminar. They look exactly the same. So what we can do is we can just take basically the final solution, or almost the final solution, just replace the molecular viscosity with the turbulent viscosity. You see also here the similarity coordinates. They're basically the same, except they're defined here with the mean quantities and so on. And so finally, let me just go to the final result. Right. So this is where we end up here again with this Z at the center line. And we see now this is basically all the same, turbulent Schmidt number and so on. But here now we have the eddy viscosity instead of the molecular viscosity. So in the laminar case, you see this was U times D divided by nu. That is the Reynolds number. But here we have U times D divided by nu T. Now nu T is not the molecular viscosity, okay? We said earlier, nu T is U prime times LT. But U prime, to some degree, is proportional to U, to the jet exit velocity. If I make the jet exit velocity 5 times larger, I will also make U prime, the turbulent fluctuation 5 times larger. And the same with L. L also, the integral length scale, the length scale of the turbulence, that scales with the nozzle diameter. If I make the nozzle 5 times as large, my turbulence scales will also be 5 times as large. Okay? So replace this here by U naught times D, and you see this here, actually, these drop out, and, it's just a constant. So it turns out so this is what this is. Turns out from experiments that this ratio here is roughly constant, which is easy to understand, and it's roughly a factor of 70. And so you see the turbulent, while the laminar case was proportional to the Reynolds number, once it's turbulent, it's actually, it does not depend on the Reynolds number anymore. The Reynolds number doesn't appear here. It's constant. Okay? It's interesting. So if I have a flame like this, I increase the Reynolds number, it becomes linearly longer. Up to a certain point, I've transitioned to turbulence. Actually, it goes down here a little bit, and then it stays constant. So everyone was right. Somebody said it gets shorter. Well, just say you said you meant this piece here. Yeah.
Also, in your experiment, what you didn't mention, you also increase the fuel mass loss rate. So you increase the fuel that you release. So of course you will increase the length.
No, because in the turbulent case, I do the same thing. I don't increase the length. The fuel. This was you said I didn't say that, but. All I do is I increase the velocity, right? And the governing equations, they know that there's more fuel, right? Because, I have a flow of z equal to 1 at a higher velocity now. So the mass flow rate of fuel is higher. But if you go to the turbulent regime, you increase this, it doesn't change anymore. It just scales then with the, basically with the nozzle diameter. That's all. Nozzle diameter, stoichiometric air ratio, and these you could say they're roughly equal to 1. So you can actually compute this roughly and look at if you have a turbulent flare somewhere, see if it roughly holds like this. Okay. Okay, good. So. I think that's all I wanted to say about this. We don't need to discuss this. So that's all I wanted to say about this. Maybe we'll take a break now, and then we'll meet back in 10 minutes from now.